There was a
Full screen. Bit full. So, and how do I change इधर से होगा? Change इधर से. Okay, okay. Okay, so good afternoon to all, and this is the most difficult session. Why? Because everybody will be sleeping. Everybody will be sleeping, and my job will be to wake you people up. And let me see whether I'll be able to do justice to it or not. Okay. So let me start with what I'll do is basically my presentation will be having two parts. In the first part, I will try to explain what basically is a geosynthetic material, and in the second part, I will try to show some applications, some projects wherein we have used this material, wherein this material has been the only safeguard or the only method of restoring the project. Okay, so to start with, let us first of all understand what is a geosynthetic material. So before we go into the details of the definition, how many of you have worked in the field, or have you used geosynthetic material somewhere? Somebody of you?
yes, sir.
You have
Geobags.
you have used geobags.
Oven, non-oven.
Oven and non. Okay. Somebody else? No. You madam, you had attended our previous lecture also. You also, I think, remember correctly. And somebody else?
He is also. We are from Goa.
You are from Bhadrapur, so you have. Okay. So okay. Okay. So what we'll do is we'll try to first of all understand what is geosynthetic material and what are the different types of geosynthetic. Like geobags, he said that we have used geobags. So geobags are created by one type of geosynthetic material called as a geotextile. But there are many types of geosynthetic material. So first of all, let us understand what is a geosynthetic material. The definition as per ASTM, American Society of Testing Materials. The definition as per ASTM states that geosynthetics is a planar product manufactured from polymeric material used for soil, rock, earth or other geotechnical engineering related material as an integral part of a man-made project, structure or a system. The points to remember here is that number one, it is a planar product. Planar product means it's a two-dimensional product. That is one thing we need to remember first of all. Secondly, what we need to remember is that it is a built up from polymeric material. So once we remember these two things, that number one, it is a planar product and it is made up from polymeric material. This means I as a engineer or I as a designer or I as an executor can ask the supplier or the contractor to give me a product based on my requirement, because this particular material is manufactured. It is manufactured. We manufacture this material in a factory. So once we manufacture this material in a factory, this means we can ask for a material which we require. And how do we require? And what are the basic components which will decide our requirement is the design components. So based on our design requirements, we will come up with certain specifications, and those specifications will define what type of geosynthetic material I require, and then I will be asking the the supplier, or I will be asking the different manufacturing agencies to supply me that particular type of material. Okay. Then second thing which we also need to understand, other thing is that it is made up of polymeric material. So what are polymers? What are polymers? Okay. Somebody can give me an answer to it. And not from the board. Not read from the board. It's easy. Let me go back in my memory lane. We go back to class 11, 12. Okay. 11, 12, we were studying chemistry. In chemistry, you are studying organic, inorganic chemistry. So that time we were studying about polymers. Okay, little bit. And that part of the chemistry we always hated. We said, okay, we should get rid of it. Somehow there are very long chains of carbon bonding with either oxygen or nitrogen or different types of elements, and we just said, okay, let us get out of it. Best is our simple inorganic chemistry is much better than it because simple formulas, some two things, one acid, one base reacting to form some salt and water. Easiest of it. Okay. So, but here again in cell engineering we get back to that chemistry part of it where we talk about materials which have come to the aid of us as designers or executors. These particular materials are there. If we see how these materials developed over a period of time, uh, first of it was polypropylene. Polypropylene, these names you need not to remember all of them. And it's not even necessary to remember when these things came into being. The only idea is that you should know that these are polymeric materials used to make geosynthetics. Why? Because once you are going to interact with people, suppose for example, you want to have a geobag, okay? And now you ask for a geobag through a certain contracting agency or a manufacturer. And he said, sir, I am giving you a geobag of HGP. And you get confused. You say, no, what is HGP? So what will happen that you will immediately say, okay, whatever be it, you just give it to me. But no, you should know it is a high density polyethylene. And once you go into the HGP means high density polyethylene, now today with the advent of internet and chat GPT, it's very easy for people to attain knowledge. If you go back maybe 20 years down the line, it was difficult to know things. I mean, it was really difficult because you need to have access to maybe the library and then you need to have the right book and then you get to the right topic. But today it's becoming very easy. So you need to know that, okay, polypropylene, HDPE, LDPE, polyesters, polystyrene, polyvinyl chlorides, these are all type of polymer materials which are used to manufacture the geosynthetic type of materials. Okay, so this was only. So now we come on to the different types of geosynthetic materials. What are the different types of geosynthetic materials? What happens? Yeah, no problem. So these are the different types of geosynthetic materials. Starting from geocells, geocomposites, geofoams, textiles, and natural geotextiles. This list also may confuse us. What is a geocell? How do I remember what is a geotextile? How do I remember what is geonet? What is a geocomposite? So, a very easy way to remember is you just divide these name into two parts. Geocell, geocomposite, geofoam, grid, membrane, net, textile, and natural geometry. Okay. So now what I need to remember? It is a cell, a composite, a foam, grid, a membrane, something net, some textile, and some natural geometry. So once this thing is clear into my mind, so now I can visualize. If it is a cell, so cell means maybe it should be three-dimensional, a little bit of three-dimensional in nature. If it is a composite means it should be having maybe two or three types of materials. Then we can call it as a composite. If we say a foam, what is a foam? So foam means it should be lightweight. So geofoam should be a lightweight material. Then geogrid means it should be a grid type of structure. In our daily life, that usually we use net for basic net we are using for mosquito net. So mosquito net. So mosquito net means we are allowing certain things to pass through it. We are not allowing certain things to pass through it. But the flow of air is easy to. So here also there should be some flows through this net. Then we are adding textile. So textile means we are using textile. We are getting textile. So textile should be something which is like a cloth. Okay. It can be different categories that we can discuss. So we can have textile means it should be a cloth. So this is how we remember it. And then natural geotextile, well, this is something which the international community accepted because in our country we have a long coastline and we have a lot of jute and coconut fiber. And so we manufactured certain geotextiles using these fibers. the coconut and the jute fibers, and international community accepted that okay, they may be considered as natural geotextiles and may also be included in the family of geosynthetics, even though geosynthetics means a material which is made from polymeric material. So still because of the contribution of our country, people have internationally accepted it that okay, natural geotextiles can also be clubbed in the family tree of geosynthetics. Okay, so with this background, we have a slight idea on what these different types of materials can be. We can also see what are the different areas of usages where we can use these materials. So, for example, I can say that I can use these materials. I'm not particularly saying a geotextile or a geonet or a geogrid or geomembrane. I am saying the geosynthetic material can be used for separation. It can be used in the areas of drainage. It can be used in the areas of filtration. It can be used as protection layer, as a reinforcement, as a barrier. These are the different major application areas in which I can use a geosynthetic material. Now, as civil engineer, when I am going to look at my project, I have to think, okay, in this particular place, suppose I want to have this particular type of application. For example, I want to have filtration type of application. And so what I can do is maybe I can go in for some sand filters, or in places where I am unable to go in for sand filters because of some construction issues, I am having a option with me that I can go in for a geosynthetic material, maybe it may be a geocomposite or a geotextile. So that option is now available with me. Let me just also go through what are the different types of these geosynthetic materials, and we try to understand them better fashion now. So the geotextiles, these are one of the major components of the major part of the geosynthetic family, and their applications are huge, and they have been used for since many years as such. These geotextiles, they are classified as woven, non-woven and knitted. Now the question comes, why woven, why non-woven and why knitted? And can I understand what is a woven type of a material, or what is a non-woven type of a material, or what is a knitted type of a material? So can somebody give an example of a knitted type of a material? Have we come across a textile which is knitted?
Knitted, knitted means our underwear are knitted type of
Inner, okay, okay. Your close, much more closer, maybe. Sweaters? Sweaters? Sweaters are knitted. Sweaters are knitted. Okay, okay, sweaters are knitted. That is one aspect. Okay, we take this, we hold it for some time. Then woven, the shirts, the cloth which we are wearing, that is a woven type. And non-woven type of material have you come across? Forget the geotextile.
plastic carry bags and plastic sheets.
Okay, yes, the non-woven bags we are there. Okay, and quilts, you understand? So quilts are also non-woven type. What we are actually having a lot of fibers. Fibers are laid on it, and then they are packed. So this is how these things can be remembered. Woven type of material means it is like the cloth or the shirt which we are wearing. The non-woven type is like a quilt type of a material where we are laying a lot of fibers. Fibers are laid in regular directions and then they are compressed to form a sheet of material, and then the knitted ones. So now I think further on it. So if I try to compare the woven type of material with the non-woven type of, okay, by simple common sense on what we have discussed, which will be having more strength, the woven or the non-woven? Woven will be having more strength. Okay, fine, great. And which will be thicker as such? Thickness? The non-woven will be thicker. Fine. So we have a woven type of material which is having more strength. and a non-woven type of material which is having relatively less strength, but it is thicker as such. So what I can do, I can use the non-woven type of material as a cushion. I can use the non-woven type of material as puncture resistance. I can use the non-woven type of material between my granular fills to protect my woven type of material from damage by puncture of the irregular shape of the gravelly material. Okay, fine. And I can use the woven type of material as a reinforcement. Okay, I can use the woven type of material as reinforcement, and I can use the non-woven type of material as protection to the reinforced layer. Okay, thereby I can come to a conclusion to derive a geocomposite which is consisting of a layer of a non-woven and a woven type of material. Okay, so that is how things are thought of. The applications are varying from separation to filtration to reinforcements, drainage, and hydraulic wear. Now, the example, I don't know whether I have included here. Okay, yes, there are certain examples. Filtration. Now, this is a classic example of wherein I can use my geotextile for filtration purpose. Shahid, have you covered the GSM part of this one? No, okay, you have to cover. Okay. I'll just give a small introduction to it. Soils are, we all know, even before we get the lecture from, soils are always weak in saturated condition and they are relatively strong in dry condition. So now if you want to construct a fill, what will be your idea? Basically, you would be trying to have that the fill is remaining in a dried state so that it is going to have its more shear strength and it is in a more stable condition. So this means if I am going to construct an embankment fill, I will always like it should be drained. It should be in a drained condition. That is why we are providing B poles. You will be seeing that all along the hill slopes, we are trying to install B poles into it so that we are trying all the water, whatever it is, in case there is some ingress of water due to rainfall, that water gets removed through the B poles. Now, the basic problems at times in big fields is that through the B poles also soil particles start coming out, and you want to restrict the soil particles. So what we do is we can install a non-woven type of geotextile over a perforated pipe. I wrap my perforated pipe by a non-woven type of geotextile and have it installed in the V pole. So what will happen? It will not allow the soil particles to move, but will allow the water to move out. Now, once this application comes to my mind, the property which I need to look at my non-woven geotextile should be the permeability characteristics of the non-woven geotextile. This means for this I have to define what is the permeability of the non-woven geotextile, as well as I should also know what are the opening space of that non-woven geotextile, because that opening space and that permeability will allow me to decide what type of material it will not allow to pass. Suppose I have a non-woven geotextile which is having an opening size of maybe more than 5 microns. Okay, let me see. Now, clay particle sizes we have studied, they are of less than 2 microns. So, what will happen? That the clay particles will start migrating out from my non-woven type of geotextile. This means if I want to use this non-woven type of geotextile in conjunction with the clay soil, I need to provide another layer of protection between the clay and the non-woven type. The answer you will say, okay, we can go in for another non-woven geotextile which is having opening size less than clay particle size. But then the permeability gets hampered. Because the smaller the opening size, the less will be the permeability. So to that I will be having my non-woven geotextile and then I can have my perforated. So the sand particles, they will be acting like a graded filter and will be retaining the clay particles and allowing the water to pass through it, and that water will pass again to the non-woven textile and output. And so my fill is in a relatively better condition of saturation I'll say it will be in a semi-saturated condition or a dry condition. Thereby we'll be having higher shear strength and the fill will be stable. Problems also come at times if we are not going to design this aspect in the correct manner. The geotextile will get clogged over a period of time, and then again I will be having particular problem of not removing of the water. Second application in the again in the road embankments, I can say these are the fascia which we are having. These are connected through reinforced sheets. Sometimes we are putting geogrid, sometimes we are putting steel strips into it. And along the vertical face of this fascia, I can install a piece of non-woven geotextile which will act as a filtration layer. Again, the concept will be the same. It will allow only the water to flow through it and not the soil particles through it. And again, on the bottom of it, I can have a drain wherein all the water which is draining out in both the directions, it is drained into it and then collected into a drain and then it passes through the main drain and it is going out. So that is how I can go. I can plan for a relatively much stable embankment or a fill. This is example of separation. Even though these are not very much related to water sources, but at times they are related to water source projects also. Because as such, if we talk about our projects, we are dealing with all types of structures. So right from buildings, canals to even roadways, and this is a problem which we might be facing a lot at times. What happens is that suppose you are having a particular road the areas because of the infiltration of water into the embankment of the road. To one fine morning, you find a pothole has started, and once the pothole is started, that is the initiation of the failure of the road. So once the pothole starts, what happens? Again, the traffic is going on. So those loads are coming, and more of this granular material is settling into the soil particles, and this fine soil is getting pumped up, and the water is going out. And this is a continuous cyclic process is happening because rains. It's not that you get rain for one day and then you are going to have a dry spell for 15 days. So you have rainy seasons for maybe 2 months or 3 months or 4 months at stretch. So this particular phenomenon occurs continuously. Now what do we do? In case we are introducing a layer of a woven, non-woven geotextile. Why here I am saying a non-woven geotextile? Here I am saying a non-woven geotextile, sorry, a woven type of a geotextile because I want to have a material which not only is allowing the water to flow through it, is not allowing the soil particles to move through it, but is also having certain tensile strength. So three components will be coming into picture when I am going to design a geotextile as a separation layer for a road. The tensile strength of the material, the permeability of the material, and the apparent opening size. What is the opening size of the geotextile? That becomes very important. So once I introduce a layer of geotextile, it will allow only the water to flow through it, and it because of the tensile strength, it will not allow that settlement to move. And because once you are confining your solid material by these layers, the settlements of roads is going to be stopped to a much extent. In fact, basically, in the start, when geotextiles were being used as separation layer in roads, many people came up with a question that this is going to be a very costly affair. And it meant to be a costly affair starting in our country because all this material was imported from different countries and and it used to be costly also. But if we talk about its advantages in the long run, is a road which was requiring continuous upgradation or continuous repair, maybe year after year, required maybe repair after 3 years or 5 years. And also one more important thing is now roads are networked to the economy also. And suppose you are going to have a bad roads, end of the day, the whole traffic, it's not the traffic which we are there, it is the traffic which is supplying essential items to many of the regions which are really otherwise cut off. Roads are the only means of transportation. So if you are going to have bad roads, ultimately the whole thing is going to be affected and leads to a greater loss of economy. So these things got introduced, and in the southern region also, and regions wherein there was a lot of rains. Here also, the geotextiles are now becoming part of the construction of the road, of the basic designs of the road. Especially in the regions of black cotton soil. Black cotton soils are soils wherein you get lot of swelling. Swelling. Swelling, what is swelling? Means there is change in the volume of the material because of change in the moisture content. Okay, so that swelling led to more cracks in the road and deterioration of the road. So there are these places, these geotextiles have been used. This is an example of a geotube. What is a geotube? Okay, tube means it's a tube. Fine. Tube means it should be having more of a lateral dimension than the horizontal and vertical dimension. That's the definition of a tube. So you have a large tube made up of a geotextile, and here we are talking tubes of the diameters of maybe some 5 meter diameter and around 10 to 15 to 20 meters to 25 meters length. So how do we use it and where do we use it? We can use it for coastal protection. So wherever there are coastal erosions, we can use geotubes. We can make embankments of geotubes. And how are these geotubes installed? You lay these tubes and then you pump in sand slurry into it. You are pumping sand slurry, so what is happening? The water is moving out and the sand gets contained into the geotube. So finally you have a structure which is 20 meters in length, 5 meters in diameter, okay, and you can keep it at that place. Rather, basically, you are first of all you are placing the geotube and then you are pumping this slurry. The water is moving out and you are having that structure. And ultimately, it will take a elliptical shape. It will take an elliptical shape. Now, suppose I have to design a geotextile. I want the geotextile which should be what type of geotextile I should consider for this geotube. I require a geotextile which will allow the sand to be contained. I require a geotextile which will be having certain permeability so that the water is moving out. And I also require a geotextile which is able to sustain the hoop stresses which are going to be there in the elliptical shape which is formed because of the moving out of the water. Because this elliptical shape, suppose this is the geotube, because of the weight of the sand, there will be hoop stresses at the lower portion of the geotube. So this particular textile should have enough tensile strength so that it does not tear. Okay. So this means the tensile strength, permeability, and the apparent opening size or opening size of the geotextile will be my design parameters to decide what type of geotextile I want to use for this particular geotube. Okay. Why I am insisting on the design parameters is that people who are not much exposed to the field of geosynthetics, they feel that okay, like suppose I say that people suppose we are using a geo bag. So they say it's only a bag. It's only a bag in which I have to fill in sand and get put it at a place. But no, actually you need to understand that what type of forces it has to resist, and accordingly you need to have that material which should have those properties. So that is the quality control which I need to see in wherein I will be deciding what type of material I am using for my geobag or even geotube or even geogrids. Now moving on to geogrids. So geogrids, as I was saying, these are grid type of materials, and because they are grid type of materials, they are basically as reinforcement. So grids means they are having reinforcement, they are having a higher tensile strength, and they can be used for Reinforcements in embankments, walls, separate stabilizations, and embankment-based reinforcements. Basically, we are having mono-oriented geogrids, bi-oriented geogrids, or multi-layered bi-oriented. So, why mono-oriented geogrids? Why bi-oriented geogrids? The question should come, why there are two different types of geogrids. These are basically based on the different types of applications. And what applications? Applications are coming on what are the types of forces which are there. For example, I am going to have an embankment. Now, embankment is going to be in one direction, okay, and the forces which will be coming will be only in the sliding mode. So, even if I go in for a mono-oriented geogrid, this will be acting, this will be fine as reinforcement element in the embankment. And how am I going to put this basically geogrid into it? Please see if I am having a okay, because it's going to act as a friction, so this is how it's being laid. You have a normal type of geotextile, some granular material, and the geogrid on it. Just I'll go forward and then come back if I'm having that question. That no, okay, I missed it. Okay, no problem. I'll just explain. Okay, so how I'm going to use geogrid as a reinforcement? Basically, if I talk about a slope, in the slope, I don't know, have you been exposed to some slope stability analysis? Slope stability, slip circle. Hmm? Do you remember? Okay. What is a slip circle? Slip circle means suppose we are having a certain slope. In case there is a failure, it will be in the form of a curve. This is how we define. Suppose this is the slope face, so maybe it will be sliding like this. We say it may be like an ice cream scoop. So that will be the slip surface. And what we when we design these slopes, what we see is that my slip circle, whichever is formed, is having a factor safety of more than 1. As per design, we say the factor safety should be more than 1.5. Okay, that's how we define the slope. So when I'm using this geogrid as a reinforcement layer, vertical, I lay this horizontally in my slope when I'm going for a reinforced earth wall. So if suppose there is a slip circle, this slip circle will be passing through these geogrids. Now failure can occur if and only if either the geogrid fails in tension or it fails in slippage. Either the geogrid slips out, then this whole soil mass will go, or the geogrid fails in tension. So now, as a designer, I require two more properties. Number one, what is the interface friction? Interface friction between the geogrid and the adjoining soil mass, and what is the tensile strength of the geogrid. With these two properties, I can design my reinforced earth wall, or I can design my use of geogrid in my slope stability. And that is how the design goes in. What I'll be getting in the design, I'll be getting what should be the length of the geogrid and what will be the spacing of the geogrid. It should be placed after 20 centimeters or 30 centimeters or 40 centimeters. So that's how I'll be doing what is the spacing and the length of the geogrid. These two parameters I will get once I do the slope stability analysis using geogrid as a reinforced layer. Okay, so next is geomembranes. So membranes, as I was saying, these should be impermeable, and once they are impermeable, this means that it will not allow flow of water through it. And once I understand it will not allow flow of water through it, this means I will be using it wherever I want a impermeable layer. And what can be that application? That application can be a canal liner. That application can be maybe the upstream face of the dam. That application can be maybe waterproofing of tunnel. So those applications are numerous. More than 30 independent individual applications are there in civil engineering which have been developed by using geomembranes in different types of civil engineering structures. Then comes geocells. So here I would like to give an example which you will be really appreciating what I am trying to say. What is the strength of water? Does water have strength? Can water carry load? Okay. What is the strength of this empty bottle? It is compressible. Zero stress. Okay. But if I fill water into it and I close it, now can it take load? Yes. So what I'm trying to say is that if you are going to confine water into it, it can take load. Similarly, the granular material. The granular material, if it is unconfined, it can take a certain load only. That will be defined by its friction, the angle of friction. Or in case it is having cohesion also, you have the shear strength. So that will be defining what will be the maximum load it can take. Which you also say in form of bearing capacity. The bearing capacity of a material. That is how we define it. But suppose I confine that granular material in the sides. It's open from top and bottom. But in the sides, if I confine it, laterally if I restrain it, then how much load it is going to take? That load will be equivalent to the crushing strength of that material. Okay? If it is unconfined, it is equivalent to the shear strength of that material. But if it is confined, it is going to be equal to the crushing strength of that material. So if you are going to have an aggregate of rock, you have gravelly material from that. That gravelly material, if it is confined, that confining will give it strength which will be equal to maybe its crushing strength. That much load it can take. Okay. So the same idea was used to develop these geosynths. These are three-dimensional open spaces. Basically, you have matrices of it, and in these geocells you can fill in granular material. Now, these geocells are confining that granular material in the way of their designs, and so they can be able to take the loads equivalent to the crushing strength. And these geocells have been used for various applications. Even they have been used as foundations in case of weak soils, and they have been also used as gravity retaining walls and making multi-layer systems. One major use the Indian Army has also put into these juices is that the heaviest tank which the Indian Army is having is the Arjun tank, the heaviest tank. And when the Indian Army has been moving in the regions of Rajasthan, it becomes very difficult to make those tanks move in the sandy regions. So the geocells have been used by the Indian Army. You lay in the geocells, you fill in sand into it, the sand gets confined, so it's able to take all that load and you are able to pass the tank, and then you just pick up the geocell and you move forward. As simple as that. The most, I'll say, the highly innovative, I'll say, it's innovation. Basically, I'll say civil engineering itself is common sense. Civil engineering is nothing, I think 99% it is common sense engineering. Remaining 1%, I'll say it's mathematics, calculations, and some designs. But most of it is common sense engineering. So geocells, you can fill in material and then you can have those loads coming on it. So you can have a geocell mattress. Suppose you are going to have some weaker foundation here, some slushy type of soil, some weak soil, some compressible soil. So you can have geocell matrices, you can fill in granular material, then you can have your reinforced earth wall built up. So these are some applications on it. Again, applications are infinite. Applications are based on how much you can think. It's your imagination. You have the material. It's your imagination. Whatever you want to think about, you have those applications. Then we have geonets. Now, geonets are also known as geospatials. Geospatials means there are three-dimensional open spaces, and through these three-dimensional open spaces, for example, if I'll just try to say, suppose I'm having my fingers like this. Now you see that these are geometries. So if suppose some water is passing from up, it can also traverse in this direction. Once if this is a geomet, so a water which is passing through the vertical gallery or the vertical opening can also pass through the horizontal opening because there is a space in between. So that's how the geomets are. And geonets you can use them wherever high seepages are to be contained or are to be channelized. For example, I am going to have a maybe basement. So okay, suppose we take this as a basement, and suppose this basement is having a lot of seepages coming in. So and maybe suppose this is the outer side of the basement, and my inner basement is this. That's the outer wall. And this is some earth fill is coming on this side. I don't want that this saturated material of this earth, which is going to be filled here, is going to affect my wall. So what I can do is I can put a layer of geonet, then I can put a layer of non-woven geotextile, and then I can have the fill on it. Now, whenever this particular region is going to get saturated, and on the bottom also we will have a collection system. Whenever this suppose soil system is going to get saturated, this water will be ultimately coming to these sides also. Will be lowering, and once it comes to this side, through the non-woven type of the geotextile, the water will pass through it, the soil will not pass, and then through the vertical forms of the geonet, this water will be traveling down. And in the lower sides, I can have some channels installed. The water gets collected there. Those channels can be led to a sump, and that water can be pumped. And this is one of the applications in which even in very deep basements, 2 or 3 or 4 level basements, geonets have been put on the outer sides of the walls, and so the basements are under much drier conditions. Then we have the geocomposites. So geocomposites, now I think by this time we are able to understand. We are having woven, non-woven type of geotextiles, then we are having geomembranes, then we are having geonets, we are having geogrids. So suppose you want to have a place wherein you want to have reinforcement as well as you want to have a separation layer, I can go in for a geogrid and a geocomposite, geomembrane, geocomposite. Okay. I can have a geocomposite which is made up of a geogrid and a geomembrane. Geomembrane will not allow the water to flow in, and the geogrid will give me reinforcement action. In case I want to have impermeable layer as well as a permeation also. One phase I want to have impermeable layer, and one phase I want to have a permeation. Then I can have a geomembrane and a geotextile geocomposite. An example, in one of the examples, I say in a dam in southern India, Kadamparai Dam was there, and a lot of seepages were happening to the dam, and it was basically in a pump storage scheme, PSP, pump storage scheme. So basically, whatever water they are losing is a direct loss to the electricity generation. So they wanted to contain the water because of that dam. So what they did on the whole of steam phase of the dam, they installed a geomembrane whole phase. Suppose this is the dam phase, the whole phase they have installed a geomembrane. For example, in this particular case, I'll say this also is a geomembrane. This particular banner is a geomembrane, but we don't know what are the tensile strength of it. We don't know what is the permeability of this. We don't know what load it can take. So what they did was they installed a geomembrane on the upstream face of the dam, and in order that whatever water is contained in the dam bottom, they installed a non-woven type of geotextile behind the upstream face, behind this geomembrane. There were two purposes of this non-woven type of geotextile. Number one, it was giving way to the water. Secondly, it was also protecting this geomembrane from being punctured because this was a stone masonry dam. from being punctured any sharp edges of the stone masonry, which could puncture this geomembrane where water is flowing. Under the head of water, if you are having a 50-meter head of water, so at the bottom part of it, the 50-meter head of water will be having a compressive force, and that compression or that compressive force can puncture the geomembrane. So, in order to protect this geomembrane from being punctured, a non-woven geotextile was installed at the head of it. Also, it was felt that maybe the flows of water may be high. So they also installed a geonet. And then to monitor whether there are certain leakages or not, they had installed some optical fiber cables between the geonet and the non-woven geotextile. With those optical fiber cables, they were able to, and there what they had put some temperature sensors. So wherever there was any lowering of temperature, this means there is certain leakage. I mean, the question is, how do you detect whether there is a leakage? Either you have some piezometer installed into it, or they have installed some temperature sensor. So wherever, suppose in this body of the dam, suppose everybody are having a temperature of maybe 30 degrees. At some certain place, suppose the temperature is 28 degrees or 25 degrees. This means some water is leaking into it. So those were the regions wherein they were then going in for repair if at all it occurred. So that is how the whole system got integrated, and the geomembrane along with the geotextile and geonet was put as a composite, a geocomposite. Okay, so if I talk about the functions versus the geosynthetic types, I say that I can use geotextiles for separation, reinforcement, filtration, and drainage. Geogrids I will be using only for reinforcement. Geonets only for drainage purpose. Geomembrane for containment. Then we also have, which are not very much popular, but we also have geosynthetic clay liners. Here what we are doing, we are having a geotextile on top and bottom, and in between some vent to net, and we form a blanket of it, and that forms the geosynthetic liner. So you lay the geosynthetic clay liner. As soon as you water it, the vent to net it swells, and it virtually acts like a blade. And installation is relatively easy. Similar conditions, similar things nowadays. People have been forming cement blankets. In cement blankets also, they have filled in certain cementitious material. On both the up and down side, there is a normal type of geotextile. For canal lining, there are a lot of usage into it. So you are just laying out the blanket and just watering it. So whatever shape it will be taking that shape because it's flexible nature. And as soon as you water it, the cement gets set, and you get a very hard surface, which is basically highly erosion resistant. And even if when the upper layer of the geotextile gets removed or it gets abraded, still that mattress functions very fine. Then we also have geopipes, and these can be used for drainage purposes, and geocomposites, obviously, from all separation, reinforcement, filtration, drainage, and containment. Then, as I was saying, natural geotextiles, we are having coir and jute geotextiles, and coir board and jute board. They have been working since very long time, working on different types of geotextiles that can be formed. The only problem with these coir and jute geotextiles is that they are natural geotextiles, and because they are natural geotextiles, so they can get they can get decayed. They can get decayed. But now the choir board, what they have come up with the idea is that they have tried to rubberize these geotextiles. So what they do is they form a geotextile, they put it, they immerse it in a rubber emulsion. So basically, you are getting a coating on it. So that's why the longevity of this geotextiles has been increasing. The question is why we should go for this. There are two things. Why at all? We are having a geosynthetic material, so why we should go for we call it the geotextiles. Well, not only they are eco-friendly, they are also cheap. They are cheap. So when compared to the synthetic geotextiles, these are relatively cheaper. As well as they are also going to give a lot of job creation is there. A lot of people are involved in it. And end of the day, the benefit of any industry is not only not to give the opening to a few people. It should be widespread. So a lot of handwork is required in these types of businesses. So it is a lot of job creations are also. And it has proved to be very effective also. Some projects were done with railway, in which coir geotextile was used as a reinforcement layer below the railway track, and it functioned very well for I think around 6 to 7 years. It functioned very well. So that was some research project which was taken up by the I think choir board or the jute board, and which showed its efficacy, because in railways we are talking about large loads. So there it showed its efficacy. Area of usages, as I was saying, roads and pavements, subsurface drainage, structural drainage, erosion and sediment control, coastal river inflood protection works, landfill cappings, canal lining, new tunnel waterproofing, and site mitigation. These are a few areas wherein we can say that we can use geosynthetic materials. And again, as I was saying, uh, you have the material. Now you have the problem. So it is your intuitiveness, your innovative thinking, wherein apart from where they are being used overall, you can find a usage to it. That is how we have always been working that way only. If we talk about river erosion, well, they are dynamic geological systems. They are ever changing, and it's really difficult to contain rivers. It's really difficult, and especially the Brahmaputra itself. It's a mighty river. It's a mighty river, and we cannot contain it. We can try to train it. And say we can try to train. Again, wherever the forces of nature are fierce, it becomes difficult for us to train. And that is why we don't have permanent solutions to it. But it also does not mean that we don't have solutions. We have solutions. The thing is that we have to optimize our solutions, because maybe if I try to totally contain it, I may come up with a solution which will be very much costly, which may not be the requirement of that time. So still we are not rich. We have to, within our resources, do the best, and that's what we are doing as such. And this is a phenomena, well, which is ever changing. There are erosions, there are depositions, and the best or the worst part is these are not constant. Regions of erosions become regions of depositions, regions of depositions become regions of erosions over the period of time. Maybe this year you find some places where there are a lot of erosions. Maybe 10 years down the line you see that those areas are regions of deposition. So this is the dynamics, the river dynamics. There are a lot of complications in it, right from it's having its own sediment control, sediment movement, river load, river engineering. These are all very complex situations. So, as civil engineers, one way is to deal with the complex things. The other way is to come out with the solutions to so as to mitigate it. So, basically, in most of the river training works, we are doing mitigation works. And anti-erosion works, they are only taken to protect the townships. We are not protecting the whole river. We are not protecting the whole waterway. We are only protecting regions where we are living. This is how the human race works. The human race protects itself only. There are jungles, we are not giving protection in, giving protection around the villages which are near the river. So that is how we are working as such. So we are working on towns, industrial areas, groups of thickly populated villages, railway lines, roads where relocation is not possible, and long lengths of vital embankments, benefiting large areas, agricultural lands where cost benefit ratio justifies the works. These are the basis or the basic premises on which we take up these erosion control works. Measures are ranging from permeable spurs to porcupines to spurs made up of bamboos or reinforced cement concrete elements. And the idea, what is the idea? The idea is simply reduce the velocity. Velocity is reduced, so the erosive forces are reduced and the sediment movement is reduced, and so your banks are protected. The simple phenomena is that only. Ways and means are changing. Geosynthetic material, woven geotextiles are available in various forms like big bags, tubes. They can be filled at site with riverbed sand to form borings, spurs, and revetments. These are the areas wherein we can use them. General approaches are there. Live planting, bioengineering, and hard armoring. Best technique will depend upon the size and location of the eroded bed. I'll not say that live planting is the only way. I'll not say it is not the only way. So it basically depends upon what is the problem we are facing, and at times when we visit certain places and we see certain failures, the first thing comes to our mind: why have they not done this? But actually, this is a continuous process. As human beings, we always try to optimize things. So you initially go in for the most cost-effective methods, and once that method does not work to your satisfaction, then and only then you go in for a much costlier method. That is how the design, the engineering, the solution are usually taken out. So it will depend upon the size, location, and the cause and severity of the erosion. This is an example wherein I just try to emphasize how we can use geosynthetic material in erosion control. Suppose this is a bank which is eroded. Ultimately, lot of movement is there. Actually, even at times there are examples wherein when we tried to control or when we had certain offtakes from the river systems because of the barrages, the offtake canals, because they had now lower sediment load, resulted in erosion of the canals. You understand? You have a barrage, you have an offtake canal. Now, at the offtake canal, a lot of sediment load or the silt load is being reduced here. So, in the canal, you are having a relatively cleaner water. But the canal in itself has to come into regime. So in order to come into regime, what it will do? It will pick up the sediment load. And that picking up the sediment load will lead to erosion in the canals. Got it? This is a classic case which is currently occurring in Farakka. The Farakka canal at the barrage, lot of silt load is being settled there. The Farakka canal is having a relatively much cleaner water. So it is being apprehended that maybe because of that much cleaner water, this canal is now, in order to maintain its regime, picking up the sediment from the river, the canal, which has led to the degradation of canal by more than 4 meters. The Farakka canal at the inflow, and there is a siphon aqueduct at Bagmati. So this reach, and there are even at some places where the scour pockets are as deep as 10 to 15 meters. Reasons are, this is one of the reasons which is being speculated. And we are working on it, CWC is working on it, Farakka barrage in itself it's working, many theories are coming out. But this is, after all deliberations, this is also thought of one of the reasons, because ultimately the flowing water, it requires certain sediment. That velocity carries a sediment load. That is what is river hydraulics. So that river hydraulics requires those sediments to move. and if you clean it enough, it will erode, and that is happening. For example, if you are going to use very good water to clean your hair, maybe your hair will get thin because it will eat up the protein layer which is going to there on your, the keratin layer which is going to come upon your hair. So this is how the nature works, and the so that's why I am just trying to say that how complex the water engineering is. So suppose you are having a hard armor system which you have installed for protection of system bed of a canal or a river system. Over a period of time, what will happen that maybe because of the flowing water, the fines will get lost, and this all these boulders or hard armor system which you have installed, they will either get settled into it or they will get washed away. So herein, introduction of a layer of a geotextile in this form will be helpful in protecting them because it will allow the water particles, the water to move out. It will not allow again the granular material to sink into it. The same example as I was telling regarding the road amendment. It will not allow this hard armor system to sink, and system will be contained in itself. This is the example of Farakka. I am saying the other example was regarding the water load, but this is where geotextile has been used as one of the major component. So Farakka barrage, I don't know, you might be knowing it's one of the longest barrage, 2.5 kilometers, and here obviously at this barrage, the river Ganges is like ocean. From this end, it's unable to look at the other end at times. And the flow velocities during flood season is around 5 to 6 meter per second, sometimes even more. And the water depth is around 25 to 30 meters during the flood season. So, end of the day, you see that at times houses are also floating when the flood is there. A lot of studies were being done, and during the satellite imageries, it was being observed that there is a shifting or meandering of the river Ganges at the Farakka branch, and it was even thought of, or even it was feared that maybe Ganges may outflank the Ganges. So then started the work of protecting the banks of the Ganges near the barrage, both upstream and downstream. And for this particular work, I'll not go into these details. There are technical details of the Rekha barrage as such. It's a 2.245 kilometer longest barrage, 126 feeder canal is there. So many anti-erosion works were being carried out. Dumping of bags was being done. Dumping of geo bags was being done. Then some live plantations were being put into it. Again, the idea was to act as deflecting spurs, but nothing of it worked. Then designs were given. Lot of designs were carried out, and this a basic design was then worked out. Typically, we designed both Center Water Commission in consultation with Farakka Barrage project, FBP. This design came out, and lot of works were done on this design also. It consisted of two layers of stone-filled wire crates, 1 meter by 1 meter by 1 meter. So cubical wire crates. Then on that another layer of 0.6 meter by 0.6 meter, 1 meter by 1 meter by 0.6 meter. Two layers of stone-filled wire crates. So a revetment was designed, constructed, laid. But each year the phenomena which I was telling used to occur. So the revetment was laid, maybe up to a length of 20 to 25 meters or 30 meters into the river system, and by the next year the whole revetment is gone. What is happening? The phenomena was simple. The sand used to get sucked out because of the flowing water, and the whole stone filled biotech used to sink into the river. And there was no method to reclaim them. There was no method to stop these settlements. And then we introduced this element of geotextile. So, State Water Commission, then some consultation was with CSMRS, some consultation was with the different manufacturers, and then an introduction of a layer of geotextile was thought of. A geotextile layer to be introduced in between here, and then here came the innovation of how do we put the geotextile below the stone filled biotech, because now there are chances that if you are going to dump the stone filled biotech on the geotextile, it will puncture it. So the innovation was, or use of the, I'll say, local material was that based on they using this bamboo, these mats are formed. They are called tarja mats. So a lot of tarja mats were used. The geotextile was fixed below these tarja mats. This was giving shape to the geotextile. It was also giving protection to the geotextile from the falling stone filled biotech. And then once this roll of geotextile was fixed with the tarja mat, it was then moved into the river using boats. It was pre-calculated that this is the bank. From this bank, some floating targets were fixed again using some boats, and this thing was laid there. Once this whole system reached the designed or the desired place, then some geobags or some bags were made to tie to on this target bed, so that once you are going to give it, it settles onto the river bed. This was all under the water. Basically, you are able to see nothing. It's only by hunches that you are going to do it. So that is why two layers were decided. That in case the single layer of stone column, the stone filled wire beds is unable to fall in place, the gaps will be filled by the second layer. That is how the whole idea was. And at the end, this portion of the geotextile, it was anchored on the riverbed in the trenches. Again, these trenches were filled with the stone filled wire plates and even geobags. So basically, what we are doing, we are securing this layer so that it does not get floated out. And now the question is that how do we join it? So we are not joining the two layers of the geotextile because ultimately they are in some certain bits only. You get either 3 meter bits or 6 meter bit rolls of the geotextile. So what we do is we have an overlap instead of stitching it, because then it becomes very difficult to handle the whole thing. So what you do, you just overlap. The idea again is that this may be 20 centimeter, 30 centimeter of overlap will not allow the sand particles to move. Again, in such protection works, you see the functioning of the whole system. The whole system, how it is functioning, and the system worked fine. The system worked fine, and then again using boats, the stone filled wire pits were just dumped into it randomly, and with certain ideas. Okay, now suppose this is my geotextile, so I'll start dumping from here, then I'll dump here this way. I know the area, I know okay, this will be my. It was all going by hunches. You cannot see underwater, it's all sediment loaded water, and that's how this whole things were being done and carried out. And finally, this is the whole system. It worked. At some places, even geobags were used, and again, these geobags systems filled up with in nylon crates. They were also dumped, and this is how final the systems under relatively much better condition as compared to the older room. Still, there are problems. Still, there are places wherein erosions are being occurring, but those regions are now reduced to smaller pockets. In the yesteryears, we are talking about maybe 12 kilometers upstream or 8 kilometers downstream. Now they are reduced to certain smaller regions, maybe ranging from 500 meter to a maximum kilometer. And those regions are also being treated over a period of time. Certain design interventions are being done, and CWC and CSMRS are continuously working on those areas. This is another example of Sarda River, the state of Uttar Pradesh. So there we were talking about, we used geotextile as a layer below the hard armor system. Here I'll just show you example wherein geobags are used as protection layers to construct a launching apron and use of porcupines as deflecting spurs. So again, because of the flood conditions and the silty type of material. See, most erodible is the silty sand, the SM type of material. Silty sands are most erodible. And finally, the river banks of the Sada river, it had lot of erosion problem. And usually what happens is that near the rivers are our villages. And the erosion was encroaching into the village land ultimately. So there was lot of unrest. The farmers' lands were being lost as such, and they were unable to feed their families also. So it was decided that okay, we go in for a construction of a launching apron using geobags. So geobags were used as such all along the length of the places where the river was being eroded, and then also to deflect the fast moving current from the river bank, porcupines were used. And these porcupines were placed on the launching apron which was created using the geobags. The launching apron is up to here, and on this launching apron you are putting the porcupines. If you are going to put the porcupine directly on the river bed, they will settle. Then further alone these porcupines will not work. So what they also did was lot of grass is being grown there. So bundles of that grass were used to fill up the spaces of these porcupines like this. So the opening spaces of porcupines were filled with this grass, and once this grass is underwater, what happens is that the silt laden water is covering this grass, which is not allowing this grass to decay. The silt laden water is protecting this grass from decaying, thereby increasing these lives of this deflecting space. So this is a photograph in the year 2011 when these things were laid there, and you will appreciate this is during the flood season. We will go little slowly. This is on 10th of June. This is on 28th June 2011, and this is on 5th July. If you see at this image a bit carefully, you will find that this is my reflecting spurs, okay, and this is more like a still water condition. So what we have done is we have deflected the high current away from the bank. That's how we have done our bank protection work. Then on 7th, okay, and so this is how these works were done. Now, with all this thing which we have now learned about geosynthetics, Let us come on to some of the advantages. The major advantage of geosynthetic material is it is cost effective. It can be designed based on your problem. You can design it. We require
how it is cost effective.
How it is cost effective? Yes, this is a good question. We took the example of the road embankment. Now, in that case, if suppose you are not introducing the layer of geotextile as a separation layer, basically I am going for the repair of my road every year. Yeah? Now, once I introduce a layer of geotextile in between, it may be costly. But initial cost may be high. But if you look at it at a period of maybe 3 years or 4 years or 5 years, so it becomes cost effective. It's like you purchase a thing which is cheap.
It's already proven.
Ah. So that's how it is proven. So I am saying, giving example, you purchase an item which is cheap but works for 1 year. You purchase an item which is relatively a bit costly but works for 10 years. So that costly item is cost effective.
So I think that used in our Indian roads. It's already proven.
Yes, yes. It is proven.
It is not possible for us. It's proven, cost effectively proven or not.
It is cost effectively proven in our country, and that is why, if you see, in many of the tenders, they are putting the usage of data styles.
Nowadays,
Yes, 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 yes. Then, obviously, it improves performance. It extends the life. It increases safety factor if you are going for a reinforced earth. It is compatible with field conditions, consistent over a wide range of soils, and relatively inert. Okay, so these are all the good things about the geosynthetics. But is it really that good? Or do we have disadvantages also? It is having a disadvantage. Number one, it requires design to assure success. It is not that we know that we are having, suppose he at a project is using certain type of geotextile, then you at your project should not just copy him, stating that okay, now he is using, so I also use. You have to see what are the forces which are going to come at your project, what are the application areas, whether I can adopt him, whether I can adopt his design as it is, or I need certain modifications on it. So it requires design to assure success. It is sensitive to UV light. This is the major disadvantage. The major disadvantage is that polymeric materials are sensitive to ultraviolet light. So what happens in it? In case of ultraviolet light, it degrades. It degrades means it will be either losing strength or it will be losing its workability. But in most of our water resources projects, especially the river bank erosion projects, it is the first year wherein your geobags are actually exposed to the UV lights. The next year onwards, it is the silt which has laid on those geobags which is protecting those geobags. Even if we go a further state further, even suppose I say, okay, some of the geobags are not functioning to my satisfaction. We have option of changing them. So it is about nothing or something. And we always say that something is always better than nothing. So we have a solution, we have a material wherein we can give solutions to problems for which we don't have the regular solutions of our engineering. Then the next question is, do we have standards? Yes, we have lots of standards, lots and lots of standards, ranging from American standards to ISO to Indian standards. And nowadays there are lots of Indian standards which have been coming into the field of geosynthetics. There is a committee TX30 of the BIS. If you can browse in through the Bureau of Indian Standard website, you go into the TX30 committee and then you can see what all the codes are there, the field of geosynthetics. So now many codes have been there, and in the Bureau of Indian Standards we are adopting, if at all we are not making new codes, we are adopting some of the codes from the ISO standard. So that's why there are lots of codes for this particular material. So that's all which I wanted to share. I hope two things I was able to do. Number one, I could make many of you baker. Nobody of you, some of them took little bit of nap, but still it was very small. And secondly, I also feel that I think I have been able to deliver something which you can carry forward. And we at CSMRS are always open for any query, any questions which you are facing. This is to all project people will say. Whenever you have any problem, do not hesitate to contact us. We may solve your problem. If we are unable to solve, we may suggest you some better place to go. That is how we do. Okay. So thank you very much. Any questions? Quick questions? No questions? Means either everything is understood or nothing is understood. Okay. Thank you. Thank you very much. Thank you, sir. Let's break with the energy of 15 minutes. Yes. इसको एक तो क्लोज हाँ स्टॉप कर दीजिए